nuclear energy. Here already we know by the graph between the binding energy per nucleon versus mass of the nuclei. Here the nuclei which are having the more mass, that is greater than of 170 mass number, then they gives the energies. They gives the energies in that fission process. Here simply fission means the larger nuclei is dividing into smaller nuclei. The larger nuclei is divided into smaller nuclei, giving the energy. This is called a fission process. The larger nuclei is dividing into the smaller nuclei and giving the energy is called fission process. In this fission process, example here in this fission process, this larger nuclei is bombarded with the neutrons, then gives the energy and also gives the smaller nuclei. For example, this neutron is bombarded with uranium 92-235, then which gives uranium 92-236 here, which gives uranium 92-236, and also which gives the smaller nuclei, that is barium 56-144 plus krypton 36-89 plus 3 neutrons. Here this is the fission reaction equation when the neutron is bombarded on the 92 uranium 92-235, which gives uranium 92-236, gives the smaller nuclei barium and krypton of atomic numbers 56 and 36, and also gives the 3 neutrons. Now here one more reaction also we have for the fission, that is this neutron 10 is bombarded with uranium 92-235, which gives the xenon and also gives the strontium plus again gives the 2 neutrons. Here in the fission process there are only 2 to 3 neutrons are releasing for every fission reaction. Only 2 to 3 neutrons are releasing for the average reaction. Here now in this nuclear energy reactions there are again this releasing neutrons are also colliding with the again uranium or the larger nuclei, then again that again gives the neutrons. Here this process is called a chain reaction. In this chain reaction, this neutrons are again colliding with the another nucleons and again gives the more neutrons, releasing the more neutrons. Here this is the chain reaction constant. K is equal to the number of neutrons released in the present reaction by number of neutrons released in the previous reaction. This is called chain reaction constant. Here this is called a chain reaction constant. If this chain reaction is controlled, then we can get the sustainable energy, and if the chain reaction is uncontrolled, then it leads to explode also. Here this fission process, based on this fission process we have a nuclear reactor. This nuclear reactor works based on the principle of controlled chain reaction. Controlled chain reaction. Here now nuclear reactor. Also in this multiplication factor K is equal to 1, then it is called a controlled chain reaction. Controlled chain reaction. If K is equal to K is less than 1, then the neutrons releasing are reducing. If this K value is greater than 1, then the more number of neutrons are releasing, the neutrons are uncontrolled. Then in this it is in the supercritical condition. Supercritical condition. Here it is in the critical condition. Here it is in the critical condition. Here in the supercritical condition, it leads to give the explode also. Right? Here this nuclear reactor works on the principle of K is equal to 1, that is in the controlled chain reaction. Here in this nuclear reactor, there is here this is the core, and for this core these are the control rods, and here this is a coolant. Here now this is the core element, and these are the control rods. And this is the steam exchanger, steam generator, and here it gives the it takes the water, and here it gives the steam is releasing from this side, and this is the diagram of the nuclear reactor. In this nuclear reactor, already we know this, in the chain reaction the neutrons are releasing averagely 2 to 3 neutrons, and these neutrons again bombarding with the heavier larger nuclei like uranium. Then this process is go on continuing. Now here this releasing neutrons, and this releasing neutrons are okay, here this releasing neutrons having the more energies. Okay, these are called thermal neutrons. Here these are called thermal neutrons. If these thermal neutrons having more energies, then they are not colliding with the fuel, and they escape from the colliding with the fuel. If the thermal neutrons having the less energy, then they can colliding with the fuel to continue the process. To slow down this thermal neutron, we'll use the moderators. We use the control rods, which has control rods. They are cadmium and boron rods. This cadmium and boron rods are used to slow down the neutrons.